Okay, now I'm calling this segment assigning participants to groups. But really what I'm going to be explaining in this segment is the difference between an independent groups or between subjects design. Those terms are completely interchangeable. And then I thought I animated it differently. And then the other option is to have within subjects design. So let's start off talking about independent groups. And the idea here is that you're going to be making comparisons between subjects. The groups are going to contain different members. So here's an example of a special type of an independent groups design, which is called a cross-sectional design. Those of you who have had any kind of lifespan development or child and adolescent or adult development may have heard these terms, or maybe you remember it from your intro to psych class. Cross-sectional research. That's where you compare a cross-section of people right now. So in the case of age, you would have a group of 25-year-olds, a group of 32-year-olds, a group of 39-year-olds. These are all individual groups of people that you're seeing in this x-axis. So in a cross-sectional design, we're going to be comparing a group of 25-year-olds to, let's say, a group of 81-year-olds. So when we look at this data here, you can see, we'll start with the little legend there. The top thing there is inductive reasoning. It's the magenta squares. You'll notice that the 25-year-olds seem to be significantly higher than the 81-year-olds. I don't know if you can see that the magenta square is actually right behind the turquoise diamond there for the 81-year-olds. And while we're at it, let's look at the turquoise diamonds, which is spatial orientation. Again, you see that same pattern where the 25-year-olds are way higher than the 81-year-olds. Perceptual speed, which is the green circles, way higher for the 25-year-olds. The numerical ability seems pretty stable. You see those yellow triangles. It looks like there's no difference between the 25-year-olds and the 81-year-olds. Verbal ability, it looks like it's lower for the 25-year-olds than it is for the 81-year-olds. And then we've got verbal memory, and you'll see that it's the orange squares, and it's the highest for the 25-year-olds and the lowest for the 81-year-olds. So when we look at this, we might say, well, it looks like for at least inductive reasoning, spatial orientation, perceptual speed, and verbal memory, that 25-year-olds are much better than 81-year-olds, and maybe that implies that with age, we would lose these skills or we would get worse at these skills. But we have to be really careful when we're making between subjects comparisons, because these are different groups of people. And so it's possible that they're scoring differently, not because of aging or natural changes, but maybe those 81-year-olds who are included in this study would have always scored differently than these 25-year-olds that are in this study, right? Like they might be substantially different from each other in some fashion. It could be level of education or health or, region that they come from, or who knows, there may be something significantly different. And that's always the risk when we do between subjects designs, that when we start off with our groups, they may not be exactly the same at the beginning. I think I talked about this a little bit when we talked about the two-group design, but we just always have to be wary that when we're going to try and make comparisons between groups of people, we have to keep in mind that maybe those groups are not fundamentally the same. Now, the correlated groups, which we talked about in another segment, also known as within subjects design, this is where the same participants are tested repeatedly. So an analogy of that from, sort of lifespan kinds of issues would be to do a longitudinal study where you have the same group of people who you tested when they were 25, you test them again when they turn 32, you test them again when they're 39, and you keep testing them across their lifespan until, in this case, they made it to 88 when we were still testing them. And now you'll notice a significantly different pattern for most of the categories. Interestingly, the perceptual speed, the green dots, is the one thing that continues to significantly decline from 25 to 81 very smoothly. There's a loss of speed. The other one that you see a decline on is that previously had been level is the numeric ability. You can see on the left-hand panel that it was pretty level across the age groups, whereas for an individual, if we follow them across their life, they are higher at 25 than they are at 88. So that's kind of an interesting difference between the two panels. But probably the most dramatic change is the inductive reasoning, the spatial orientation, which is the other one that had declined, verbal memory. Those things had shown a very steep decline when we looked at cross-sectional data, and they appear pretty level for an individual across their own lifespan. And so when you're making this kind of within subjects comparison on the exact same test like this is, it really underscores the idea that if the groups are not equivalent at the beginning, then between subjects research can give us an incorrect impression of differences between groups. So I just thought I'd share this visual to help drive home the idea that, if we can do it, if it's a subject that lends itself well to a within subjects design, it's a lot more powerful for actually revealing exactly what the pattern would be for individuals. There are some limitations we talked about before. Some kinds of topics we can't test in a within subjects design because once they've experienced the test once, if you give them the test again, they may just give the same answer, not because they actually still feel it, but because they remember what they said before. That's a huge risk. We call the participants tainted in that situation. Like, well, they already experienced one condition. We really can't test them again because they're now tainted, and they're going to give an answer that's not, necessarily, organic. And so, we want to use within subjects designs whenever we can. It's not always going to be possible. So I thought I'd give you some examples from an area of research that I've always been interested in, which is our memory for pictures versus words. And here's a nice 1971 study where they actually assigned different people to all 6 of the conditions that you're seeing in this graphic. So you have the P is the people who were labeling the picture that they saw. So they see a picture of a dog and they say dog. You've got the people who see the word dog, the concrete noun, and that's the C's. And then the people who saw an abstract noun like justice, and they had to say that word out loud. And that's the A's. And so you have those 3 groups, and they got a fast presentation rate. And then you have over on the slow presentation rate, the exact same groups. They just all happen to be right on top of each other. And so you have the exact same categories. The thing is, in all 6 of those groups were different people. And interestingly enough, in 1971, it was 8 people per condition. Now, if you multiply 8 times 6 groups, that's a total of 48 people. So random assignment should have produced a good, reliable, any individual differences should have been spread out across the groups and all those things that we talked about with the benefits of random assignment. But 8 is a pretty small group. The fact that they're seeing a meaningful, and I should say a significant pattern is probably meaningful in this, even though it's only got 8 participants per group. Because if you're seeing a difference with only 8 people, and it's a good significant difference, it implies that they were all very homogeneous. They all scored very similarly to one another. And so we can have pretty good confidence that this is actually what the pattern is. But I thought I'd throw this in here because you could go as crazy as these people did and have all 6 of these groups different. What I would have done if it were me in the more modern era is that I would have had a group of fast learners, and they named the pictures, they read the abstract word out loud, they read the concrete noun word out loud, they did all the conditions, versus the slow learners. I might even do it entirely as a within subjects design, where I have, for part of the study, it's a fast presentation rate, and for part of the study, it's a slow presentation rate. And some of the stimuli are pictures, and some of the stimuli are abstract words, and some of them are concrete words. Like, I might do the whole thing within subjects today. Back in 1971, very common to do between subjects designs. So each symbol represents a different group of participants is basically what I wanted to illustrate with that one. This one, same subject, different study. In this one, they had, actually this is called a mixed design because they had the same, the rate of presentation was a within subjects variable. So you see presentation rate across the x-axis. So some of the materials were presented with only 113 milliseconds exposure, and some were as long as 333 milliseconds, so a third of a second of exposure. And then their job was to name the picture or name the word, recognize the word, whatever. They had their tasks they were supposed to do. And so some of the participants had pictures, some read a word aloud, and some had to recognize something. So they did a mixed design where one of the independent variables was within subjects and the other independent variable was between subjects. So that's another way that a person could design a study. You don't have to have just within or just between. You can do a mix. And that's another power of the factorial design, right? You can have this mixed model, growing the confidence that the participants are performing consistently and realistically, and all the things we want. So how do we make sense of the interactions that we're exposed to? Well, hopefully I've emphasized this with the examples I've shown, but the definition of an interaction is that the effects of one independent variable depend on the specific level of the other independent variable. So here's an illustration from some medical literature. What they were interested in this is whether energy drinks in combination with other things are associated with ER visits. Along the y-axis, you see that it says ED visits because that's emergency department, and apparently this is from the UK. So on our x-axis, we have our one independent variable, which is males and females. So the independent variable is sex, male or female. And then the other independent variable is combination. And so in all cases, they consumed energy drinks. And then in the blue bars, it's energy drinks plus alcohol. In the light blue bar, it's illicit drugs plus energy drink. And then the gray bars are pharmaceuticals plus energy drink. And I thought this was a good example of a couple of different concepts. One is that typically when we're reporting interactions, we do it in bar graphs because generally we have independent variables that are categorical, and so it doesn't make sense to do line graphs. In the previous illustrations that I showed you, you'll notice that they used line graphs, and that's considered incorrect in modern APA style because, for example, the one on the left says fast and slow. The fact that they used a line graph means that it implies that there's something between fast and slow. Like those aren't categories, those are some kind of continuous variable, and that's not what it was. And so they've gotten away from these line graphs and instead have gone to these bar graphs that indicate that these are separate and independent data points. So it is just alcohol and energy drink, and that's why it is a blue bar. If we had drawn a line between these three data points, it would kind of imply that you could go from alcohol combination, slide somehow into illicit drug combination, slide into pharmaceutical, and that just doesn't make sense. Okay, the other thing I wanted to illustrate though is that let's just look at the blue bars for a second. So for the males, 20% of the ER visits were energy drinks combined with alcohol. For females, 10% of the ER visits were for that. 12% of the males' visits to the ER were for illicit drug combinations with energy drinks. And for females, that was 5%. But look at the ratio. If they had only studied alcohol and illicit drugs, we might have gotten the impression that sex didn't really matter. Like basically, the males and the females came at basically the same proportion to the ER because of alcohol or illicit drug combinations with energy drinks. Thankfully, we have the pharmaceutical combinations in there to clarify that it's much more likely that females come to the ER for pharmaceuticals than for either of the other causes. Whereas for males, they're almost equally likely to come for alcohol combination or pharmaceutical combination. So sex does matter. So by having these two independent variables, we're actually able to sort out that it's your sex and what you combined with energy drink that seems to predict your likelihood of going to the ER because of energy drinks. So again, the power of the two independent variables reveals itself in our ability to sort this sort of thing out. And you can really see what I mean by that definition of the effects of one independent variable depend on the specific level of the other, right? So knowing that you are female we see a different pattern than we see if we know that you're male. All right. Now there's another way that researchers will depict interactions, and that would be in a table. And this is again an old-timey one from the early 70s, and it's again in that picture word literature. Actually, I think it might even be from the same. Yeah, it's from the same one that I had shown you, where they had that mixed model where they had. So here we have what had been on the x-axis is now over here on the far left called rate. So we see that 113 milliseconds all the way up to 333 milliseconds. Picture target, naming target. So that means it was a word. Anticipations mean they're saying it before they really saw the thing. And this is where they said the wrong thing. So we've got anticipations, we've got misses. What I want to attract your attention to are the misses. So let's just look at the rate of 113 milliseconds. We see that the picture target, they had 0.19 misses, whereas the naming target, they had 0.31. So that 0.31, well, sorry, I just whacked my microphone. That 0.31 is larger than that 0.19. I think we can agree to that. But now when we start putting it in context, we start thinking, well, maybe that's not that 19 versus 31. How about this next row? At 167 milliseconds, we have 0.06 misses with the picture versus 0.21 misses with the name. So now we're seeing that picture target miss rate was really high at the 113 milliseconds level. Because now we keep going down and we see, wait, the miss rate keeps going down, right? And it gets down to basically the floor by 250 milliseconds. So they're really not making any mistakes from 250 milliseconds. Really, I'd say 167 milliseconds on, they're really not making any mistakes. It takes with a name target all the way till 250 milliseconds before they're basically not making any mistakes. So we're seeing all of our misses in the 113 milliseconds rate for both picture and name. And then for the 167 milliseconds, we're still seeing it for the name. So that shows you that knowing that it's a picture or a word and what rate of presentation helps us to explain those circumstances when pictures are an advantage versus names, right? So we're seeing more misses when it's naming. So this isn't a graphic. This is you being able to look with your eyes and see, wait, I see, and I highlighted it to make it a little bit easier. Okay, wait, these three groups are different from the rest. And, you know, if all three of the groups had all been under name, let's say all three of my yellow highlighted had been under name, we would say, well, you know, type of target seems to really matter, but rate of speed doesn't really matter for the picture target at all, right? But because we're seeing it across picture and names, and then we're seeing it across a couple of different rates, we're seeing, okay, apparently both independent variables really matter. Okay, so here's a little exercise I like to do in class. Clearly we can't do it live, so if you want to, you could pause me. And your job will be to figure out, based on this, these are 20, what you see in that purple matrix is 20 different studies where the participants were either male or female. So at the top of the column, I put a female sign with a question mark. If the participants were all female, then it says yes. If the participants were all male, then it says no. The next column says emotional question mark, and what they were interested in is whether the participants were displaying emotions during the study. And so if they were emotional, it says yes. If they were not, it says no. Okay, now the researchers who are doing this big meta-analysis to try and see the big pattern of whether females really are more emotional than men or not, they were trying to figure out, are females more emotional than men? So you're going to be trying to figure out from that little matrix, this is basically what they distilled down in the data that they relied on. You're going to try and figure out whether women were much more, somewhat more, slightly more, equally, slightly less, somewhat less, much less, likely to be emotional than men. Okay, so you can pause me and try and calculate it out. Otherwise, I'm going to just keep going. Okay, so either you rejoin me or we're keeping going. So here's how you would figure it out. You make a little matrix. Now in this case, the matrix it is still called the factorial matrix, but instead of containing averages or means like it had in the previous matrices that I showed you, this is going to contain just counts. So we would use a slightly different statistic to analyze this data than we would the ones that contain averages. But guess what? This isn't a stats class, so I don't have to talk about that. Yay! I just wanted to tell you these are not averages. These are counts. Okay, so were the participants female? Yes or no? And were the participants emotional? Yes or no? So to fill in that top left cell, I'm going to look for all the rows that say yes and yes, and that turns out to be 12. Then I'm going to go through and look for all the columns where it says no and then yes, and that was 3. So we had 3 studies where the participants were not female, but they were emotional. Then I'm going to look for all the yeses and nos. So yes, they were female, but no, they were not emotional. And then I'm going to look for all of the no-nos, which is no, they were not female, and no, they were not emotional. All right, so we've got, went ahead and summed them up just so we see that we have 16 studies that had female participants and 4 studies that had male participants. So clearly people were much more interested in studying females, weren't they? This is one of those areas where we could say people's biases can lead them to design studies in ways that can support those biases rather than looking at males, which would have been the falsification attempt, right? They were always overarchingly looking at females. But anyway, the question is whether women were more or less or equally likely to be emotional than men. So let's get back to that. So we've got 12 out of 16 studies where the females, we've got female participants who were emotional. 12 out of 16 studies, the female participants were emotional. For the males, 3 out of 4 studies, they were emotional. So if we do the little ratio on that, 12 out of 16, 3 out of 4, that's equal, isn't it? So this is a really super simple one. We don't have to compute any statistics to confirm our interpretation that they were equally likely to be emotional. There are statistics that we could run if this was closer together, but I think when you see that they are exactly the same number, there's no real reason to run any statistics on it. 3/4 equals 3/4. I'm going to very confidently say they were equally likely to be emotional. So there are lots of ways that we can kind of break down the patterns in data and look at the effects of 2 independent variables interacting with each other. All right, let's go ahead and take a break right now. My dog is whining and wants out, so I will come back and see you guys in the next segment.